Alright, greetings everybody, and today we are back with some more complex analysis. Today we're evaluating the improper integral from negative infinity to infinity of 1 over x squared plus 1 dx. So this is probably an integral you've come across already. If you like solving integrals like me, it's going to just evaluate to pi, just a singular pi by itself. Usually the method is just to use some trig sub u something, turn this thing into an arctangent or something like that, and plug the bounds in, you get pi. But I want to use complex analysis today because we like complex analysis. So let's just dive straight in. So complex analysis, we have this integral thing right here. It would be nice if we can introduce a new complex valued function for us to integrate over. So what I'm going to do is I'm going to let some new complex function. So let's say, for example, f of z, there's some complex function right here, be equal to the integrand right here, but now we have complex valued inputs. So pretty much we're going to have 1 over z squared plus 1. So just changing this x to a z right here. So we have our function right here now, and later on we're going to be contour integrating this thing over a contour. And if we want to do that, it would be nice if we can use Cauchy's residue theorem. So in order to use that theorem, we need to figure out where the poles of this function are, because if we know where the poles are, then we know where to integrate across and all that. So we need to figure out the poles of this function pretty much. And where exactly do those occur? Well, it's exactly where the denominator equals to 0, because when the denominator is 0, then everything blows up. So pretty much we want to solve for when z squared plus 1 is equal to 0. So just standard way of solving this, z squared is equal to -1. And then taking the square root on both sides, square root of -1 is just plus or minus I. So plus or minus I in this case. So we know that the poles of our function occur at plus or minus I. So let's actually just draw that up on a little diagram. So if this is our complex plane right here, we have the real axis and the imaginary axis. I'm just going to mark the poles in red. So we have poles at plus or minus I, so those are just going to occur right here. So this can be negative I, this can be positive I, for example. Hopefully the red comes up clear on the camera. So those are where our poles are, and now that we've got that out of the way, we want to figure out where our contour should go through, or what our contour should be. So you see, we want to integrate this function f of z right here, and ideally we want to capture this original interval that we have right here from negative infinity to infinity, because if we integrate over that thing, then we pretty much get this integral back. And also one more thing, I forgot to do this from the start, but let's just call this integral I, just so we know what we're solving later on. So this integral is I. So as I said before, we want to capture this interval from negative infinity to infinity, but let's actually just consider the finite case of that first. Let's consider some interval from negative r to r, where r will become a really, really big number once we take the limit. So on our diagram right here, let's actually just draw the contour in blue. We want to start at some point r, negative r for example, and we want to end up at some positive r like so. And we want to start at negative r, and we want to integrate on this line right here on the real axis. So this is kind of like the first path that we want to integrate across, from negative r to r. And if we integrate across that thing and take the limit as our r approaches infinity, we're going to match up with this interval right here. So we have that interval now, and we want to turn this into a contour somehow. So that means turning it into a loop. So how can we turn this into a loop? Well, we don't want open ends or anything, we want to close them. Well, remember, as I said before, we want to use Cauchy's residue theorem. So ideally, we want to enclose one of these two poles right here, and we're just going to choose the positive pole in this case. So how can we enclose this pole? Well, we can just use a simple semicircle. So if I draw up a semicircle that goes all the way up here and back down, notice that this whole contour right here encloses this pole, so we're good to use Cauchy's residue theorem whenever we can. And let's actually just name these parts something. Let's call this whole entire contour C, and let's call this arc that goes up here gamma. Okay, and gamma is just a semicircle with a radius of r. So now we know what our contour will look like. Let's actually write things out a little bit. So remember, we want to integrate this function f of z over this contour. So all we can write is that we want to find the contour integral over the function f of z like so. dz. And what exactly is this contour right here? Well, we can actually decompose this contour up into separate parts, just like we can with real integrals, where we can kind of chop up the integral and integrate over each of those little sub-intervals pretty much. So we can do the same thing here. This integral over the whole entire contour is the exact same thing as, first of all, the integral from negative r to r. And now notice that we're on the real axis right here. So we actually don't need to use f of z, we can just use f of x because we're kind of treating x as a real variable. So just f of x because we're on the real number line, dx. And then we can add that with, let's rub this out, we can add that with the integral over this arc gamma right here. So we can add that with the integral over gamma of f of z dz. So f of z because we're in the complex plane now. So this is kind of the equation we have right now. And later we're going to be taking the limit as our r approaches infinity. And in the limit, this thing will actually turn back into an I. So we'll worry about that stuff later on. But first of all, let's try to figure out what these integrals will evaluate to one by one. So let's start with the contour integral over c. So contour integral over c. What exactly is that? Well, remember, this contour encloses this pole right here, this pole I in red. And we can use Cauchy's residue theorem for this one right here. And what does that theorem say? It just says that it's equal to 2 pi I, so this integral right here is equal to 2 pi I times the sum of the residues of our function f of z, like so. And notice, we're actually going to have only one residue because we only have one pole right here. So this is basically the same thing as 2 pi I times the residue evaluated at this single pole. So evaluated at z equals I of a function f of z. Okay, and we need to figure out what this residue is, this residue at z equals I. And let's actually just use the definition of the residue. So what is the residue? The residue is nothing but the limit as z approaches this pole, so as z approaches I, of z minus the pole, z minus I, times the function f of z. But notice f of z is exactly this thing up here. So it's going to be 1 over z squared plus 1. So now this thing right here, this is the limit we need to evaluate now in order to find a final value for our contour integral, for our residue. So how can we evaluate this limit right here? Notice that if we plug I into here, this numerator is going to go to 0, and if we plug I into this denominator right here, well, I squared is -1. -1 plus 1 is 0, so we're going to have a 0 divided by 0 situation, which means we have to use L'Hopital's. So actually, we actually don't need to use L'Hopital's, we can just algebraically manipulate this thing a little bit. Well, you could use L'Hopital's rule if you want, it really doesn't matter, but we can have 2 pi I times the limit as z approaches I. And now notice that bottom right there, that's just positive 1 is basically the same thing as negative, the additive inverse of 1, which is -1. And what is -1? -1 is exactly I squared. So we can have z squared minus I squared on the denominator like so. And this is basically a difference of perfect squares. So we can write this as z minus I over, now the denominator will turn into z plus I, and z minus I like so. And notice, this factor and this factor will cancel each other out, leaving us with the limit as z approaches I of z plus I. And this z right here, in the limit, that's just going to turn into an I, leaving us with 2I on the denominator. So we're going to have 2 pi I, and then this limit's just going to evaluate to 1 over 2I like so. And the nice thing is, these 2's right here will cancel each other out. These i's will cancel each other out, leaving us with pi. So what exactly did we just find out? We just found out that this value right here, this pi, is exactly the value of our contour integral over c of our function f of z. So that's quite nice. We've evaluated one of these integrals. And just a quick note right here. Later we're going to be taking the limit as our r approaches infinity, which means this whole contour integral right here, or this path, this contour, you can imagine it as growing bigger and bigger into a really, really big semicircle. And you might be wondering, well, if we change the value of r? Wouldn't that change the value of the contour? But the thing is, with Cauchy's residue theorem, as long as this contour encloses this pole, the value will still stay the same. So we can take the limit as our r approaches infinity. That contour will still enclose the pole I. Therefore, we're still going to have the answer of pi. So we can deform the contour as much as we want. This contour integral will still evaluate to pi. So that's a key note there. So we just found, let's actually just put all of our results under this line right here. So on this line, I'm going to be putting the results in the limit as our r approaches infinity. So first of all, this integral right here will evaluate to pi. Okay. So that is one of our integrals done. We can maybe put a tick right there because we're done with that one. So on to the next integral. Next, we're going to be having a look at the integral from negative r to r of just our f of x. So integral from negative r to r of f of x dx, like so. Let's just plug in the definition of our f of x. Well, this is the integral from negative r to r. F of x is 1 over. Now remember, here is f of z, but if we plug x into here, we're going to get x squared plus 1. So 1 over x squared plus 1, like so. And well, what would happen if we take the limit as our r approaches infinity? So in the limit, as our r approaches infinity, what are we going to get on this thing right here? We're going to get the integral from negative infinity to infinity of 1 over x squared plus 1 dx. But notice, this thing right here is exactly the integral we started off with, which we defined as I. So in the limit, as our r approaches infinity, on this integral right here, the integral from negative r to r, we're just going to end up with I, like so, just our original integral. So that's our second integral figured out. So we can put a tick right there. And on to our final integral. And this one's going to take a while to evaluate because we actually need to prove that it's equal to 0 in the limit. So yeah, let's start here. Integral over gamma of f of z dz. This is the integral over this curvy path here, this semicircular arc thing. And whenever we have an integral over any path really, we would like to parameterize it because it just makes things easier. So let's just call this integral, I don't know, j for now. And j is equal to the integral over gamma. F of z is exactly that thing, 1 over z squared plus 1 dz. And we need to parameterize this thing right now. So what I'm going to do is I'm going to use a substitution because I think that's the easiest way to parameterize this thing. Because notice, z is always on this curve right here. And what exactly is that curve? That curve we can define it as some r, so this is a radius of r, times e to the I theta, where our theta is between, let's see, 0 and pi. So 0 and pi, like so. And notice this parameterization here, right here works because e to the I theta is the circle. We're scaling it up by some value r, which gives us a circle of radius r. And our theta is going from 0 to pi. So it's starting at 0 right here, an angle of 0, and it's going to go all the way to pi on the other side. So this parameterization works, z equals r e to the I theta. And if we plug this in, it's all good. We just need to figure out what our dz is equal to. So differentiating both sides, dz, derivative of this side is ir e to the I theta d theta, just standard derivative stuff right there. So now we can chuck all the information into our integral. So now our integral j is going to be equal to the integral over that new interval, so integral from 0 all the way up to pi, of now we're going to have 1 over z is this thing, r e to the I theta, but we're squaring it right here. So r e to the I theta, but the whole thing squared, is exactly r squared times e to the 2I theta. So down here we're going to have r squared e to the 2I theta, and then we're going to have plus 1. dz right here turns into I r e to the I theta d theta. So nothing too difficult there, just chucking that in. Alright, so now we've successfully parameterized our integral j. And now we want to prove that this thing goes to 0 in the limit as our r approaches infinity. And to do that, we need to estimate this integral a little bit. And to do that, let's just chuck absolute values outside of our j. So let's do a new section right here. If we take the absolute value of j, that's going to be equal to the absolute value of this thing right here. But notice we can actually bound this thing by using the integral inequality, because right here we're dealing with a real variable, just theta. Theta is a real variable. So we can say that it's less than or equal to, the absolute value of j is less than or equal to this integral, but inside we're going to put absolute values everywhere. So this is less than or equal to the integral from 0 to pi of the absolute value of the whole entire integrand. So we can have absolute value, let's just chuck all this junk on the top. So I r e to the I theta over r squared e to the 2I theta plus 1, and yeah, that should be it, d theta like so. And we can split the absolute values up a little bit right here. If we split it onto the denominator and the numerator, absolute value of I right here, that's just going to give us 1. Absolute value of r is still r, and absolute value of e to the I theta is going to give us 1 as well. So in fact, this integral, we can just bring this r out to the outside, because remember, r is going to be a really, really big number. And strictly speaking, actually, I forgot to put this in the very start, but r is strictly greater than 1 because we don't want r to be less than the distance from the origin to one of these poles, otherwise we wouldn't be enclosing these poles. So I want r to be greater than 1 pretty much. So r is always positive, so absolute value of a positive number is still positive. We can chuck that out to the outside because it's just a constant in terms of theta. And now we're left with the denominator pretty much, because the numerator is just going to be 1. So how can we deal with the denominator? We're going to use something called the reverse triangle inequality to show that it's less than or equal to something else actually. So reverse triangle inequality or inverse triangle inequality, what does it say? It says that the absolute value of the difference of two complex numbers, let's call it a and b, doesn't really matter. So absolute value of a and b, that's actually greater than or equal to the absolute value of the differences of each of the individual moduluses. So, or moduli, I think that's the plural of modulus. But yeah, we have this theorem thing right here. And how can we use that to further estimate this integral right here? Well, notice we have this positive 1 right here, which we don't really like. We ideally want a negative. But notice positive 1 is the exact same thing as negative, the additive inverse of 1, negative 1 like so. And now notice we have some complex number minus another complex number, so we can throw it into that formula. So in this case, our a is r squared e to the 2I theta. So right here we're going to have r squared e to the 2I theta, and our b is just negative 1. Okay? And we just need to plug it into this formula right here. So our absolute value of a is just the absolute value of r squared e to the 2I theta. So what's the absolute value of that thing right here? Well, we can split the absolute values up inside here. Absolute value of e to the 2I theta is just 1 because we're on a unit circle, just some complex number on the unit circle. Then we have the absolute value of r squared. R's number, positive number, greater than 1. So absolute value of r squared is just r squared. So this absolute value of a right here just turns into an r squared, like so. And minus the absolute value of b. b is negative 1. Absolute value of negative 1 is just, well, 1 itself. So we've just found that this denominator thing right here is greater than or equal to the absolute value of r squared minus 1. But remember, r is greater than 1, so the smallest r can be is 1, or just a little bit above 1. 1 minus 1 is just 0, so this thing is actually always positive, so we can ignore the absolute values. That's quite nice. So we've just found that this denominator is greater than or equal to r squared minus 1. But that doesn't really help because we want to bound this integral from above. We want to show that it's less than or equal to something else. But the nice thing is this thing's on the denominator. So in fact, if we kind of reciprocate both sides, we're actually going to flip this inequality sign. So what do I mean by that? If we have 1 over the absolute value of r squared e to the 2I theta plus 1. Since we're reciprocating this thing right here, we're going to flip the inequality. So now this is less than or equal to 1 over r squared minus 1. And we can plug that directly into our integral right here. So this is less than or equal to, remember r is going to jump down to the front, so we're going to have r integral from 0 to pi. And this whole integrand right here is going to turn into 1 over r squared minus 1 d theta, like so. And the nice thing is, r squared minus 1 is independent of theta, so let's chuck that out to the outside as well. So this is equal to r over r squared minus 1 integral from 0 to pi of d theta. This integral is pretty easy to evaluate, it's just pi. So we're going to have pi r squared minus 1, like so. So what exactly did we just find? We found that the absolute value of j is actually less than or equal to this thing right here. It's absolute value of j less than or equal to this thing. So remember, we want to take the limit as our r approaches infinity. So let's actually just take the limit on both sides right here. If we have the limit as r approaches infinity of the absolute value of j, that's going to be less than or equal to the limit on the other side. So limit as r approaches infinity of pi r over r squared minus 1, like so. And notice, if you evaluate this limit right here, it's going to give you 0, because this denominator right here, this r, has a degree of 2, whereas on the top right here has a degree of 1. Or you can just use L'Hopital's rule for that. Differentiate the top, you're going to get pi, or just 1. Differentiate the bottom, you're going to get 2r. Take the limit as our r approaches infinity, and you're going to get 0, because the denominator is going to dominate the numerator. So this limit right here actually in fact goes to 0. So what does that mean? That means that limit as r approaches infinity of the absolute value of j is less than or equal to 0. But notice one thing right here. The absolute value is always positive, and the only way for a positive number to be less than or equal to 0 is if it's actually 0 itself. So we just showed that the limit as our r approaches infinity of the absolute value of j, that's going to give us 0. And well, the only way for the absolute value of something to be 0 is if that something itself is 0 in the limit. So this implies that the limit as r approaches infinity of j is equal to 0 actually, because the only way for this thing to work is if j is equal to 0 itself in the limit. So what did we just find? Remember, j is exactly this integral over gamma right here. So what should I rub out? Let's just rub out this whole thing right here. Basically what we just showed is that if we take the limit as our r approaches infinity on j, or the integral over gamma, that's going to give us a 0. And that's the last integral. We've just showed this integral goes to 0. So we've evaluated this final integral right here. Let's clean things up a little bit over here. So in our equation right here, this integral will just evaluate to 0 in the limit as our r approaches infinity. So this integral pretty much just contributes nothing to our whole entire contour. So there we go. Alright, time to wrap everything up, because we've basically solved every single integral. So in the end, what did we find out? As you can see, right here we have pi being equal to I plus 0. This implies that our I is equal to pi. And well, in the end, I, remember, was our integral from before. So integral from negative infinity to infinity, 1 over x squared plus 1 dx. That's going to give us pi. And that is the final result for today's video. This integral evaluates to pi in the end, and we use complex analysis to show that. So yeah, that's a pretty nice result. I like this integral a lot actually. Yeah, hope you guys enjoyed this video actually. I always like doing complex analysis videos, it's always pretty fun to do. Yeah, as I said before, I hope you guys enjoyed it. Make sure to subscribe, like, comments, do whatever you want. Share this video everywhere if it helped you or if you found it helpful. Yeah, hope you guys enjoyed. Have a wonderful day, and I'll see everyone later. Bye bye.